for this problem, we're dealing with a rolling bowling ball, and it's going down a return ramp at the side of the alley. The ramp is inclined at an angle beta to the horizontal. What's the ball's acceleration, and what's the friction force acting on the ball? So to begin with this problem, we're going to have to realize that we do have to solve for the inertia in this case. So for the inertia, we would take a portion of what we know in the previous example. So we do know in this case, let me draw it out a bit. This is our bowling ball, and then it's going down a ramp that's sort of this way. It's inclined, it's like an inclined plane. The angle beta is working here, and then this is how we're making this angle. It's like this, and then the acceleration is equal to r times this. And then we, of course, have the mass of the bowling ball. So we're not given any value in this case except the inertia. We do know that the inertia is equal to 2/5 times the mass times the radius squared. And we do know that the equation for the acceleration, which in this case we're trying to find it in the x direction, would be the radius times alpha. So now, we have to move on to finding the sum of forces and the tension. So the sum of forces in the x direction can be found by doing the weight times the sine of theta, which is the angle that we're trying to find here. This would be the sine of theta. And then minus the friction force, which is static friction in this case. And then this would give us the mass times the acceleration in centimeters. And then if we try to find the total torque force, we know that it's the friction, the static friction, times the radius, and that's equal, right here, we're going back here, that's equal to the inertia times this. So that's from here and here. And then this will give us 2/5, and times the radius squared, and now times the acceleration in the x direction over the radius. So we're simply taking the inertia and multiplying it by the acceleration over r. So now let's move on here to continue solving this part of the problem. Let me move it over here. So now we do know that the static friction is times the radius, and we put our equation of the inertia back here. Mass times the radius squared times the acceleration in the x direction. Sorry about this, it's not squared in this case, I forgot. And now we could divide both sides by r and get rid of our radius, and we're going to be left with the static friction is equal to 2/5 of the mass times the acceleration in the x direction. And now we have another equation that we can use in this case, is the weight times the sine of beta, which we didn't finish solving this one, minus the static friction. So this is the static friction that we found, so it would be 2/5 the mass times the acceleration in the x direction, and now we're going to be left with the mass and the acceleration in the x direction. And so ultimately we're going to be ending up canceling these masses, and we're going to be completely left over if we cancel out all the masses with the acceleration in centimeters in the x direction is equal to 5/7 times gravity times the sine of beta. So that is ultimately our acceleration. And then, as we found previously, if we were to use this, we now know that the static friction is equal to 2/7 of the weight times the sine of b. And that's after we plug in this value, because now we know this value, and we know that the friction force, the m, times that value of the acceleration, so we would have just plugged that in here. We would plug this value in here, and it would have given us this. So that's our friction force, and that's our acceleration.